So before we start today, just saw an interesting piece of news. If I don't know if you guys are also following, you might know that there was this undersea volcanic eruption, right, in the Pacific Ocean, and basically that caused a tsunami. And this small island in the Pacific Ocean, close to New Zealand, the country's name is Tonga. So it was devastated because of this volcanic eruption and the subsequent tsunami, right? And it caused a lot of damage, and they're still sort of recovering from it. So I don't know if you guys followed this news over the past week. But one interesting thing that happened due to this was actually, so there was a undersea fiber optic cable which was running to Tonga. Okay, so there are these fiber optic bundles, right? So like bundles of optical fibers encased into a strong cable, and they are laid underneath the ocean. And this is how like countries across the world are connected to each other, continents, and we can all access the internet from anywhere, right? So there are, I think, 400 of these really high capacity fiber optic bundles, which are sort of laid down all over the ocean. And one of these is going to Tonga, okay? And this actually broke due to this volcanic eruption. And so basically the entire island was cut off from the rest of the world. So they had to, at least for the first few days, they had to sort of deal with this devastation themselves. There was no contact. Nobody could even access any mobile network or any internet on the island. Okay, and then slowly, sort of after a couple of days, New Zealand sort of sent some help, and then they set up some basic like 2G network, but still, sort of the usual internet service is not up there, and it will take. And they're saying like a couple of weeks or maybe up to a month to repair this. Right, so basically the whole cable is broken, and now you have to go undersea, and then sort of there's these specialized vessels which can go and then you repair these cables. So something relevant to what you're studying in this course, right? So you can see this technology is actually very important, and yeah, so this was a big factor in Tonga not being able to access or ask for any help from the outside world because they just lost all contact. Okay, so larger countries like Europe, US, and India, there are a lot of these, not just one, but there are a lot of these intercontinental cables coming in at various points. So even if one of them break, it's not too much of an issue. Of course, the capacity goes down, but you can use the other ones still to communicate. But for these small countries like Tonga, there is only one, and then that broke, and they were sort of isolated. Anyway, so if you've not seen that, maybe you can just Google it up and read more about it, and how it's interesting how they identify these faults and fix these fiber optic cables under the ocean. Anyway, so yeah, so last few classes basically we were discussing the linear characteristics of the optical fiber channel, right? So attenuation and dispersion. These are linear characteristics because, as we saw, basically they don't change fundamentally the power spectrum of the signal, right? So they don't transfer any energy between frequency components. So attenuation just causes loss, like so the overall power, the spectrum is scaled by some number, and the overall power is dropping. In the dispersion case, basically you're just applying a phase shift to the different frequency components, right? So the power spectrum is unchanged. That's why they are linear effects. So starting today, we'll discuss some nonlinear effects in the fiber, right? Which can also lead to distortions in your signal, especially at high data rates and when you're using multiple wavelength channels. Okay, so these nonlinear effects can scatter power from one particular frequency to another different frequency. It can generate new frequency components, and so, for example, crosstalk between different wavelength channels, etc. Okay. So okay, so another way to sort of distinguish linear from nonlinear is that, so for linear, if a system has a linear response, then it does not depend on the input power or energy in your input, right? So for example, in the attenuation case, there's some loss coefficient, and which gives you like by how much fraction the signal is reduced on certain propagation length, and that's independent of my input power, right? Like, it just gives me the fraction by which you lose power. Similarly, for dispersion, it does not depend on the power in my input pulse, right? The dispersive effect just depends on sort of temporal and spectral properties, right? Like my pulse width and the fiber dispersion properties, or refractive index with frequency, right? It does not depend on the input pulse energy or power. Whereas nonlinear characteristics actually depend on the input power, right? So the response of the medium now is dependent on the input power, right? So that's another way to sort of distinguish linear and nonlinear. So one thing is that these nonlinear effects scale with intensity, right? So you said that the response depends on the power or the intensity in my input, and typically the effects scale nonlinearly with the change in the input power or intensity, right? So there are a couple of useful concepts that are defined while studying nonlinear effects in general. Okay, so one is known as the effective interaction length, L effective. Right. So we know that when we launch power into an optical fiber, for example, if you look at the power versus distance, right? So it falls exponentially because of the linear attenuation that we discussed, right? So there is some input power here, P in, right? And there is an exponential decay here, so E of Z, right? Where alpha is the attenuation coefficient, right? And nonlinear effects, as we see, basically they depend on the power, right? So the effects are enhanced when you have large power, but when the power reduces, the nonlinear effects go down. Okay, so you can see here that the power is varying with propagation length. So in the initial part here, there will be strong nonlinear effects, but once the power has decayed, the nonlinear effects would sort of be subsided, become unimportant compared to the linear effects. Okay, so instead of now like trying to calculate at every position, what one can do is sort of do an averaging. Okay, so what we do is compute the area under this curve, right? Because so you know the equation of this is just an exponential, so we can integrate this function and find the area under the curve, right? So we find this area under the curve here, and then just equate it to this input power okay, times some effective length here, L effective. Okay. So what we are saying is that the cumulative effect of these different powers along the length is sort of equivalent to a constant input power over this effective length, right? Which is of course smaller than my fiber length, right? And this effective length basically gives is calculated basically, yeah. So you take the integral of the area under this curve and just divide by p. So it's this the side of this rectangle here. Right? So it's it's some measure of basically the effective length over which nonlinear interactions are important, right? So basically, we are saying up to L effective, nonlinear effects will be important. Beyond L effective, they won't be important. So, I mean, we can just compute this actually, right? So, Pz we already know is just this form, right? And P is a constant, so it will come out in this cancel here. So, if you do this integration, you'll see that this just comes out to be, okay, so this doesn't go to infinity, right? Sorry. So, you have some fiber length L here. So, L is the total fiber length. So, we go to L. So, if you do this integration, this comes out to be this. Okay. So, if this L is large enough such that alpha L is much greater than 1, then this term is small, right? And L effective is just 1 over. Okay, so for long links, so typically beyond like 100 kilometers, the L effective now is independent of the length, right? So as I'm increasing my fiber length, this L effective is not changing at all, right? That just tells you that the power has decayed so much that now nonlinear effect is not, or they are negligible, right? So,
P
so
input also be there.
P input gets cancelled, right? Here. So this has to have units of length, right? So you can see here, so alpha, of course, has units of per length, right? So you can see, so this is our units of length. Right, so actually, so if you put, so typically alpha is 0.2 dB per kilometer, right, at 1.55 micron. So of course you have to convert from dB per kilometer to just simple per kilometer here, right? And then when you take this, so 1 hour alpha is about 20 kilometers. Okay, so once your fiber length is exceeds sort of beyond that, so like once you go beyond 50 kilometers or 100 kilometers, then basically this factor here, e to the minus alpha L, does not contribute at all, and your L effective is now basically 20 kilometers. Right? Right, so you can see that as you increase the fiber length, so basically if I plot, for example, L effective versus L, okay, so initially it will start increasing, right? So for small alpha L, you can see here, I can take e to the minus alpha L as 1 minus alpha L. So then I just get alpha L in the numerator, and then alpha gets cancelled, so I just get L. So for very small lengths, L effective is just L, right? And then for large lengths, it sort of saturates to 1 over alpha. Right, and typically, like for optical communication networks, we're talking about long link lengths, right? So tens of or hundreds of kilometers. So basically, L effective is just 1 over alpha. Okay, so that's the effective length over which nonlinear interactions are taking place. They don't take place over the entire fiber length because sort of it scales with how much power you have in your signal. Okay, so one thing to note here is, so typically for very long links, what we do is we place amplifiers periodically along the link, right, to compensate for this loss in signal, right? So let's say typically for a very long link, there is some amplifier spacing here, so you have some length LA of fiber between the amplifiers, right? Your total link length is L, right? And you have roughly, let's say, any number of amplifiers. Right, so so typically once you go beyond sort of 100 kilometers, then you have to start placing amplifiers. Okay, so typically this amplifier spacing here is between, let's say, 50 to 100 kilometers. Okay, so typically, like if you look at these undersea cables, typically like every 80 kilometers or so, there is an amplifier. Okay, so you can see that this length scale here is much bigger than this 1 over alpha, right? So basically what is happening, so if I launch some input power here, it's decaying along the length, right? And then I have an amplifier, so I boost it back up. Okay. And then it decays again over the next section, and then the next amplifier boosts it. Okay. So for each section between the amplifier here, there's an effective length, just like this, right? So each of these sections are independent now, because at the start of each section the power is boosted back up. So now for such a case, the total L effective, right, will be the number of sections times the L effective of each section, right? And so typically for these lengths, the L effective for each section will just be 1 over alpha. So if you have a certain number of amplifiers NA in the link, then the L effective goes up scaled by the number of amplifiers, right? And why that is happening is because every amplifier is now increasing the power back up again. So now nonlinear effects will again start happening, right? So just if you have amplifiers in the link, then you have to keep track of the amplifiers. Okay, so that's the first concept, effective interaction length. Okay, the second concept which is used to sort of calculate nonlinear effects is effective area, A effective. Okay, so this is called effective mode area. So again, nonlinear effects scale with the intensity in the optical wave, right? And you know, intensity is basically the power in the signal divided by the area over which the wave is propagating, right? So in an optical fiber, basically, you know that sort of so if you talk about single mode fibers mostly, then basically the fundamental mode has some mode profile like this, right? So if I plot the intensity profile or the power profile, that goes like this, right? So basically it has some, so of course the core has some size, core radius A here, right? And this mode has some extent given, so depending on the wavelength, right? So we already discussed this briefly, right? So for example, for this fundamental mode, you can well approximate this by a Gaussian function, right? Where W is the waist of this Gaussian, right? So or the one over E square intensity half width, right? And this W we saw depends on, for example, the wavelength or the V number, right? So for a given fiber, it depends on the wavelength. Right? Generally, it depends on the V number. So again, so this is now, if I now plot sort of the mod square of the electric field, or which is proportional to the intensity, right? So that looks like a Gaussian function here with radial distance, right? I mean, to be more exact, this is a Bessel function, right? But for the lowest order LPG mode, it's well approximated by Gaussian. And again, just like the L effective case, so instead of if you had to calculate nonlinear effects, basically since they depend on the intensity of the power, right? So at each point here, the effect will be different, and then we'll have to calculate at each point and integrate. Right. So again, we do a simplification. We basically do find the area under this curve, right, and then find an effective sort of radius here. And we can say basically the intensity is constant up to that radius, and then zero afterwards. Okay. So this A effective is computed as, so we take the integral of the mod square over area, right? So since this is like a circularly symmetric case, so for example, you can take an area element which is like a small ring here, right? And then so this would be like r dr d theta, and then integrate r from 0 to infinity and theta from 0 to 2 pi. Okay, so we basically define the square of the integral of e square over area divided by integral of e to the fourth over area, right? So you can see that so here e square and then whole square. So we have e to the fourth in the numerator and e to the fourth in the denominator. So those cancel out. Here I have an area square. I have area here. So this has units of area. Right, and you can easily compute this. So you can do this for any complicated sort of mode profile, right? But in case for this fundamental mode in the single mode fiber, you can approximate this by Gaussian, right? So if we take ER to be just a Gaussian, then we can compute this integral exactly, right? And then you can see that this actually just comes out to be pi W. So just the waste of the Gaussian here, that basically pi W, that's the effective radius that we get. Okay. So, right, and basically what we say is that the effective intensity which is giving me the nonlinear effect, I can just say is the power in my signal divided by A effective, right? So I'm just computing this number here. So I integrate, I find the total intensity and just divide by the effective area and say that the intensity is constant over that effective. Okay, so instead of finding the effect at each location, basically we just integrate over the fiber cross section and say that I can just take an effective intensity and then compute the nonlinear effect like that. Okay. Right, so if you take again a standard single mode fiber, so recall again there are these relations. So given single mode fiber, so W over A is some function of the V number. Okay, so we saw there was some polynomial formula here in V. So and V for a given fiber just depends on wavelength, right? Depends on the cross section side and the index contrast. So this typically comes out to be about 70 to 80 microns square. for the telecom wavelength. So between, let's say, 1.3 and 1.6 micron. So the conventional single mode fiber which is used. That's the number for the effective mode area. Okay, so basically the nonlinear effects scale with, of course, intensity, right? So for a given power, they scale with inversely with the effective mode area, and then they scale with length, but not with the total length, with this effective length that we saw, right? So basically, the strength of the nonlinear interaction, right? If you take a fiber, if you take some fiber, then from the fiber parameters you can compute. So from the loss coefficient you can compute L effective, and then from this mode parameters like the index contrast and the V number, you can compute the A effective, and the nonlinear strength basically for the fiber goes as L effective divided by A. So the larger this number, stronger will be the nonlinear effect in that fiber. Okay, and if you suppress the nonlinear effects, then we want this ratio to be small. So large A effective and small L effective would reduce your nonlinear. Okay, so yeah, so these two concepts are important to keep in mind. And now, if you look at specifically the nonlinear characteristic, the specific nonlinear characteristics, we can sort of divide them into two categories. So one is stimulated light scattering, where basically what happens is that the light interacts with the molecular vibrations in the medium, in this case silica glass, right? And due to this coupling, basically light is scattered from the incident wave frequency or wavelength that I am sending to another different frequency. Okay, and the frequency shift corresponds to basically this vibrational frequency of these molecules. Okay, so that's called stimulated light scattering. So that's the first type of nonlinear interaction that can happen. Okay, so basically, yeah, let's say you have some fiber, you take inside the silica matrix, there are some of these molecules which are vibrating. Okay, so the SiO bonds are vibrating, and then when I have some incident light at some particular frequency, let's say omega p, then due to the coupling with this vibration, it scatters the input light into a different frequency, omega s. Okay, so this omega s is not equal to omega p; it's typically less than the incident frequency. Okay, so basically, part of the energy of the input photon is taken away by these vibrations, and then the rest of energy is scattered away as another photon. Okay, so this is also called inelastic light scattering, because the energy of the scattered photon is not equal to the incident photon. So recall when we were discussing this linear attenuation, there was this Rayleigh scattering, right, which was basically determining the loss coefficient of the fiber. And Rayleigh scattering is basically elastic scattering, where basically the scattered photon has the same frequency as the incident photon, right? So that was Rayleigh scattering coming from, as we had discussed, that inhomogeneous density, because this is an amorphous material, right? And that was basically determining the propagation loss. So here in the nonlinear case, this light scattering is inelastic. Okay, so the scattered photon has a different frequency. Okay, so light scattering is one type, and then there is another type of nonlinear effect, which is called a parametric nonlinear effect. So in this case, you can see energy is exchanged between the optical field and the vibrations in the medium or phonons. In the other type of nonlinear effect, what happens is that the medium just acts as an intermediary, right? And basically, light energy is exchanged between different optical fields. So the medium doesn't end up either gaining or losing energy. It just acts as an intermediary to transfer energy between different optical waves. Okay, so that kind of nonlinearity is called a parametric nonlinearity. And for optical fibers, there is this nonlinearity known as the Kerr nonlinearity. Okay, so that's the other type of nonlinearity apart from light cycles. So that we'll discuss later. First, we'll discuss light scattering. Okay, so depending on the type of these vibrations which couple to the light, this can be classified into two. So one is SBS, stimulated Brillouin scattering. The other is SRS, stimulated Raman scattering. Okay, so Brillouin and Raman are named after the scientists who discovered it. Of course, you already know about C.V. Raman. And so, basically, the difference between these two is the type of vibrations which couple here. So, in the Brillouin case, so this difference, right? So, this molecular vibration has some frequency capital omega, okay, which is equal to the difference in the incident and the scattered frequencies. So in the Brillouin case, this vibration is typically low frequencies, so they are known as acoustic phonons. So for silica in optical fibers, that's about 10 gigahertz. These vibrations. Okay, so there's a 10 gigahertz separation between the scattered and the incident wave. Whereas for Raman scattering, this vibrations are at much higher frequency, so-called optical phonons. Okay, so these are typically 10 terahertz, so 13 terahertz for glass, roughly. Okay, so you can see that there's like a 3 orders of magnitude difference here in the vibration frequency. Okay, and so there is a frequency shift here, right? Along with that, there is also bandwidth around this frequency shift. Like, so it's not exactly 10 gigahertz, but some frequencies around 10 gigahertz. So I'll put sub B here for Brillouin and R for Raman. If you look at the bandwidth here, so delta FB, that's typically quite small, so less than 100 megahertz. Okay, so it's a very narrow band effect. Whereas for Raman here, we'll see in glass, it's very broad band. So delta FR is actually a few terahertz, almost 10 terahertz. Okay, so the center is 13 terahertz, but it's also spread over a very wide band, few terahertz. Whereas here it's a very narrow band effect. So it's sharply peaked around 10 gigahertz. Okay, so these are scattering by acoustic phonons or sound waves, right? So you know that you take any material, like you can excite pressure or sound waves through those medium, right? So these sound waves, basically, if you excite them in a fiber, that's what causes Brillouin scattering. Whereas Raman scattering is caused by optical phonons, right, which are more sort of localized high frequency lattice vibrations, which was first discovered by C.V. Raman when he was looking at scattering of light from different media. Okay, and then there is this word stimulated here, right? Stimulated, right? So basically, these effects are present all the time, but typically, again, because they're non-linear, they scale with intensity, right? So as I increase my input power, for very low powers, they are in what is known as the spontaneous regime. Okay, in the spontaneous regime, what happens is that randomly, once in a while, some photon from the incident field gets scattered like this. Okay, most of the power just goes through because the interaction is weak at low powers, right? And once in a while, there is some spontaneous scattering. So that's the spontaneous regime. As you keep increasing power, what happens is that eventually you reach so-called stimulated regime, where what is happening is that your input field itself now causes these vibrations, right? And these vibrations are causing the scattering. So there's like a positive feedback which starts happening. Your incident wave causes the vibrations causes the scattering, which increases, right? So the scattering feeds back to the field, which feeds back to the scattering. So something like what happens in a laser, for example, right? So you have some gain medium in a cavity, you excite it using some external energy pumped into the system, right? At first, below threshold, you just have what is known as spontaneous emission, right? Once in a while, some excited atoms in the cavity emit photons. But as you keep increasing the pumping, at some point you cross threshold, right? And then what happens is that the emitted photons now cause more photons to be emitted from the medium, right? You go into the stimulated region. So it's similar here. Okay, so we'll discuss each of these one by one. So let's start with Brillouin. Okay, so basically SBS is happening because, so when I have a strong electric field associated with some optical field propagating here, right, that causes some pressure gradients in the medium due to this phenomenon called electrostriction. Okay, so this is a coupling between the intensity of light and sort of the density or pressure in the medium. Okay. So high intensity of light here causes some pressure gradients or density gradients, which are basically sound waves, right? Sound wave, as you know, is basically just a pressure gradient which is traveling. Right, and you can imagine now if you have some density, right? So you take this optical fiber, right? You have some input wave, optical wave. So typically the input wave is known as the pump wave in the nonlinear optics literature. The input wave is typically known as the pump wave. Okay, so that's, let's say, at some particular frequency omega p, right? And due to this electrostriction effect, basically now you have some pressure gradient or density gradient, right? So it looks like a grating which is alternating regions of high density, low density, high density, low density. Of course, the difference in the density here is very, very small. Okay, so the normalized to the average intensity, it's about, let's say, 10 to the minus 8 or 10 to the minus 9 or something, very small. But still, over long lengths, the effect accumulates to a large effect. Okay, just like, for example, when we discussed, for example, polarization mode dispersion, we saw, right? So even a very, very small birefringence, but accumulated over long length adds up to something significant. Something similar happens here. Okay, so basically you have these pressure density gradient, which is now moving at the speed of sound in the medium. Okay, so this is like a moving grating, right? So density changes leads to refractive index change, right? So we know that the refractive index in a medium is directly proportional to the density of atoms. So there is a small variation in the density that leads to a small change in the refractive index. So this looks like a grating, right? A grating is nothing but a periodic variation of the refractive index. So this is like a moving grating. So this is moving at the acoustic velocity. Sound velocity. And so now anytime you have a wave incident on a grating, you know that depending on the Bragg condition, there can be a small, there can be a significant reflection, right? If you satisfy the Bragg condition, right? So basically, again, what happens is that this incident wave is seeing this grating, and due to this grating, there's a strong reflected wave in the backward direction. Okay, and because this grating is moving, right? So for stationary gratings, we know that the reflected light has the same frequency as the incident light, right? But since this grating is moving, right? So you can think about it's something like a moving source. It's like a Doppler effect, right? So the backscattered reflected wave has a smaller frequency than the incident wave. Okay. So this backscattered or back reflected wave is known as the Stokes wave. Okay. So basically the frequency of this backscattered light is slightly lower than the input frequency, shifted by an amount, what is known as the Brillouin frequency shift, FB. Right, so this is omega b that we talked about here. So FB depends on the material properties. Okay, so FB basically, so is the frequency of this acoustic wave here. Okay, so it depends on the refractive index of the medium, the acoustic velocity, right, the velocity of the sound wave, and then the wavelength of the input light. Okay, so this is known as the Brillouin shift frequency. So typically, if we take glass, right? So refractive index we know is about 1.45. Acoustic velocity, sound velocity in glass is about 6 kilometers per second. Okay, so if we take my input wave to be again, let's say 1.55 micron, this FB Brillouin shift comes out to be 11 gigahertz. Okay. Or if you calculate this frequency shift and calculate the Stokes wavelength, right? So the Stokes wavelength will be larger than the pump wavelength, right? So lambda s minus lambda p here comes out to be about 0.1 nanometer. Okay, so let's say my input wavelength is 1550 nanometer exactly, then the reflected light is at 1550.1 nanometer. Okay, so basically what's happening is that the power in my forward propagating signal is getting back reflected to a slightly different wavelength, right? So in terms of communication, right? In terms of sending information to a receiver, basically you can see that what's happening here is that my power is getting back reflected here instead of reaching the receiver, right? So it almost acts like a loss channel to my signal. And so you might think that it's a very small effect, right? Like these index variations are quite small, and so this coupling between the light and the sound is very small. But again, we are talking about kilometer lengths, right? So over a large length, these effects build up, and you can get quite a big reflection back. Okay. In fact, you'll see that for moderate input powers, you can quickly reach a situation where most of your power is reflected back, right? And hardly anything reaches the receiver. Okay, so if you look at the frequency domain, what's happening? So let's say if I'm plotting with respect to the optical frequency here, mu. So my input is at mu p, right? Is C over lambda p. So it's getting scattered to a lower frequency. Okay, so this mu s, the Stokes frequency, so this difference here is LB. And also it's just not scattering to a single frequency, there is a certain bandwidth associated with the scattered frequencies, right? So this bandwidth here, delta FB, that's given by the inverse of the phonon lifetime, right? So basically, let's say you excite like a phonon or sound wave excitation here, and then you see after how long does it decay, right? So there is some lifetime associated to this phonon once you excite it before it decays. So that lifetime is TB. So this TB is the lifetime of acoustic phonon in glass. Okay. So the longer this lifetime, the narrower this bandwidth. So typically in glass, this lifetime is about microseconds, or like tens of nanoseconds to a microsecond. So this delta FB comes to be the bandwidth for the Brillouin typically is in the range 50 to 100 megahertz. This, although it's finite, it's quite small. It's 50 to 100 megahertz centered at a shift of 11 gigahertz. Okay, so you can see that this shift is quite small, right? So for example, recall that so we had this WDM grid, right? So there was this DWDM grid where we have different wavelength channels that we can send simultaneously data on each of it, simultaneously to the fiber, right? And so these wavelengths were separated by 100 gigahertz, right? So the DWDM grid. Right, so here you can see that basically the signal is getting scattered to a frequency about 10 gigahertz below, right? So let's say if you take this channel, it will get scattered 10 gigahertz below, so it is still far away from the next channel. Okay, so basically SBS doesn't lead to any crosstalk between the different channels, right? It just acts like a loss mechanism for one individual channel. Right. So if you have multiple channels propagating, each channel influences experiences its own SBS, right, which acts like a loss. So it doesn't lead to any crosstalk between the channels. Whereas when we discuss Raman, because of its broadband nature, right? It leads to crosstalk between the channels. But for SBS, it's acting on each channel individually, right? And just acting like a loss. Okay, so this profile here is basically like is what is known as a Brillouin gain profile, right? So scattering is maximum at the center here when the separation is, let's say, exactly 11 gigahertz. But when you start moving away from the Brillouin shift, the scattering intensity goes down. Okay, so right. In other words, basically, if I send two signals simultaneously, let's say I send a strong wave at this particular frequency, the pump frequency, and then I send another weaker optical wave at this Stokes frequency. Okay, so both of them are separated exactly by this Brillouin shift. Then what will happen is, due to this scattering, this Stokes field will start experiencing gain, right? Because pump photons are scattered into the Stokes. So the Stokes field will start experiencing gain. Okay, so this profile is basically known as the Brillouin gain profile, right? So it tells me how much gain I'll get versus frequency of the Stokes, right? So we can approximate this well by a Lorentzian function. Okay, so peak gain here is some GB, and the width here is some delta FB, right? So this can be, and remember the center is at FB. Okay, so I can approximate this gain profile like a Lorentzian function like this, and of width delta FB and center FB. So I mean, you must have seen this Lorentzian function in many other places already before. Right. So basically, what is happening, right? As I increase my power in this input wave, right? So this is my input pump wave. Okay. So due to this electrorestriction mechanism, it gives rise to some small acoustic wave here. Right. Initially, it might just be some spontaneous. Right. So this in the spontaneous regime where you have some small excitations, photons popping up here and there. So there's a question: in what perspective is SBS causing loss? Right. In terms of if I'm at the receiver and I'm sending pulses from the transmitter, right? So I expect to receive these pulses at the receiver, right, which is carrying information. But what is happening here is that because of this SBS, instead of this pulse reaching the receiver, it's actually back reflecting and going back towards the transmitter, right? So at the receiver, I won't receive anything or very small, right? So in terms of what is reaching the receiver, right, it's like a loss. I'm sending this much power, but I'm hardly receiving it. So in that sense, I'm saying it's a loss, right? But the power which is at my frequency that I'm sending the signal omega p, right? That keeps reducing because the power is getting transferred to a different frequency. But anyway, yeah. So from the communications perspective, right? It's acting like a loss. Right. So yeah. So it gives us to some small like phonon excitations or a very weak
Sir,
acoustic wave. Yeah.
sir, only the power is reducing, or some interference is also coming due to reflected waves?
Yeah. So I'm coming to that. Right. So let's say so I start with my input wave that due to this electrostatic effects excite some phonons or some weak acoustic wave. Right. So due to this weak acoustic wave, there is a small amount of this backscattered Stokes wave. Right. Right. So now if you have a forward propagating wave at omega p and a backward propagating wave at omega s, right? So now there will be some interference between these two waves, right? And basically, so for example, if you know that, so if you have two waves at the same frequency counter propagating, it leads to what is known as a standing wave, right? Because of the interference, basically you get regions of high intensity and low intensity, right? And basically there is no energy propagating anymore, it's just a standing wave. So here, basically the frequencies are slightly different, okay? So again, you can calculate the interference, and what the interference is basically, it's again like a regions of high and low intensity, but now it's not stationary, it's not standing, but it's moving at this same velocity. Okay, so you can calculate the wavelength difference, the frequency difference is basically at b, right? So it's traveling at this same speed, right? So now you see that there is this intensity grating which is set up because of the beating between the beating between these two. Again, due to electrosection, increases my acoustic wave amplitude, right? Because basically now you have again regions of high and low intensity. Now it's also moving at the speed of the acoustic grating. So basically you can see that it will excite more phonons, right? It will excite or increase the amplitude of the acoustic wave, right? So this is the stimulated process that I'm talking about, right? So the acoustic wave leads to backscattering, and the beating of this backscattering with the input wave leads to more acoustic waves, which leads to more backscattering, right? So basically you start stimulating the process, just like in a laser, you initially have spontaneously emitted photons. At some point when you keep increasing the pumping, these emitted photons now cause more emissions to happen, right? Cumulated emissions. And basically the cumulative effect of all of this is like a constructive interference in the power direction. Similar effect here, right? Okay, so this positive feedback, as you increase the power, basically this positive feedback can really exponentially increase this backscattering, right? Just like in a laser, you keep increasing the pumping, right, up to the threshold. Basically, you see a very small output, and then suddenly at threshold, like you see a very large output. Okay, similar is the behavior here, right? For low pump powers or the low, this scattering is weak and you don't see much back scattering. Then up to a certain threshold, beyond which you suddenly start seeing like almost, let's say, 100% of the power being reflected back. Okay, so this coupling between the pump and the Stokes waves can be modeled in simple sort of propagation equations, right? And the coupling between this pump and the Stokes wave is given by the strength of this Brillouin gain factor. Okay, so I didn't tell you. So FB and delta FB we discussed. This peak gain factor here. So in glass, this is about, this is 5 times 10 to the minus 11 meter per watt. Okay, that sounds like a small number again, but you'll see that it can lead to dramatic effects at reasonably low powers. So, yeah, so this coupling, right? So, if I look at the intensity of the pump wave, IP, how it's propagating, right? So, it's losing power to the Stokes. So, right? So, there's a negative sign here. So, the intensity is going down in the pump wave as it's propagating due to the Brillouin interaction, right? Whose strength goes as the Brillouin gain coefficient, which is a material property, times the intensity of the pump and the intensity of the Stokes. Okay, so this is the nonlinear part here, right? This is a nonlinear function of density. And then you can also include linear loss if you want, right? That is the usual linear propagation loss. And if I write for the Stokes, which is the backward traveling wave, so it's traveling in the minus z direction. So this is z. It's traveling in the minus z direction, right? So there's a minus here, right? And the Stokes experiences gain due to the same Brillouin interaction. So it has a plus here. Right? So the Stokes amplified as it's traveling. And again, we could include linear loss. Right? And the intensities here of the pump and Stokes are essentially the power carried in the respective waves divided by the effective area of the fiber. Okay. So basically, we can use these equations to, for example, let's say if I launch a pump wave at the input here with some particular power, and I launch some Stokes wave from the other end, right? Basically, what happens is, so if you see, the pump wave, of course, starts like it decays like this, right? And the Stokes waves gets amplified like that. Right? So this is pump traveling in the forward direction, and this is Stokes. Oh, should be reversed. Because of course the pump has higher power. The Stokes cannot exceed the pump power, right? Okay. So you can see basically what can happen is that, so if this is my input power, a large fraction of it can just get back reflected into my transmitter, right? And at the receiver, I'm receiving a very, very small amount of power. Okay, and of course, in the actual like communication setting, I'm just sending power from the transmitter, right? I'm actually not sending anything from the other end. So we can see that again. So this effect will sort of happen up till L effective, and then beyond that, this nonlinear effect will die down, right? Because the pump power has now become very small. Right, so once the intensities pump intensity becomes small, then this term becomes small compared to the linear term. Right, so only up to L effective roughly, basically this term is important. Okay, so because these are nonlinear coupled differential equations, it's hard to solve them analytically. But, so typically you can solve them numerically. And so basically a rule of thumb is that so there's a as I keep increasing my input power here, right? So if I define a reflectivity here, right, which is basically the Stokes power that I measure coming into my transmitter divided by the pump power that I send. Right? So typically, again, this reflectivity shows like some threshold behavior. So up to some power, and then suddenly it shoots up, okay, beyond a particular threshold power, and it can reach like 100%. So reflectivity of 1. So this threshold power, so this shape you can calculate by again numerically solving these equations. But a rule of thumb is, so this threshold power is roughly about 21 times effective area divided by Brillouin gain times L effective. Okay, so basically once my pump input power exceeds this value, right? If it's higher than this, then I'll get almost 100% reflection back, right? Or in other words, this at the receiver will go down to almost 0, right? In other words, I don't even need any input from the Stokes side. A very, very small input, some spontaneous noise, right? Some single photon spontaneously emitted somewhere or some background noise can get the Stokes started, and then it can amplify so much that 100% of the pump power is transferred to the Stokes by the time it reaches the transmitter. Okay, so basically beyond this input power, I mean there's no input of the Stokes from the other side. Just if I exceed this input power, just starting from the spontaneous noise, the Stokes power can amplify to such an extent that I get almost 100% of my pump reflected back. Okay. So you can see that this factor is coming here, right? So we said that the nonlinear strength is typically L effective by A effective, right? So you can see that this threshold power is inversely proportional to L effective by A effective, right? So if L effective by A effective is larger, which means the nonlinear strength of the fiber is larger, then this threshold power will be lower, which means like this backscattering will occur earlier, right? Because the nonlinear interaction is stronger, right? So that this factor is coming. And of course, it's also inversely proportional to the material which has a stronger Brillouin interaction will have a larger GB here, which means this threshold power will be small. Okay. So again, we can put some numbers here for the standard SMF that is used. Right, again, so we discussed already, A effective is about, let's say, 80 micron square, 70 to 80 micron square. L effective is about 20 kilometer, right, for 0.2 dB per kilometer loss. GB is 5 times 10 to the minus 11 meter per watt. So this comes out to be about 5 right? So that's a really small amount of power, right? 5 milliwatt is like 7 dBm or something, right? Yeah. So a few milliwatts, that's a really small amount of power, right? Typically, so these are the kind of powers that are used in the semiconductor lasers at the transmitter end, right? Typically, we want to send just to compensate for the losses here. And at the receiver, typically the photo detectors have sensitivities in the microwatt range. Okay. So typically from here we want to send at least milliwatts. So you can see that if we exceed even 5 milliwatts here, then basically all of my signal will be back reflected and nothing will reach the receiver. Okay, so this is actually a very big problem, right? So the initial days of the optical fiber communication, this was a big bottleneck. Right, so if your powers are limited to lower than 5 milliwatts, then depending on the receiver sensitivity, the minimum power that you require here, your link length is limited, right? Because there's only a certain amount of loss you can take here. So this was in the first sort of 2 generations where optical fibers, optical amplifiers were not invented or used yet. Right? So this is actually a very big problem. Okay, so how to overcome this? Right, because this can severely limit my link length. Okay, another way to see this, what this threshold behavior is causing here is that, so if I plot, so the power at the receiver here that I'm getting, so basically the pump power reaching the receiver here versus the power at the transmitter end. Right, so the power sent from the transmitter, which is the input, the pump power sent from here. Right, so initially for low powers, as I increase my transmitted power, the receiver power also increases. Basically, only linear loss is happening. Right, so as I increase, so there's some fraction of power which is reaching the receiver, and that fraction remains the same. Right, so as I increase my transmitted power, my received power is also increasing. So this is the linear regime. Right, and that's some after this threshold thing. Basically, any increase in power is sort of back reflected, and I don't get any gain in the received power. Okay. Whereas if you look at the back reflected power, so if I look at the back scattered or the Stokes power, again here at the transmitter end, so that's very low for up to this threshold here, and then it suddenly shoots up, right? And then beyond the threshold, as I'm increasing my transmitted power, all of it is just getting back scattered, right? So the back scattered power just keeps going up with input power, whereas the received, so this is the received power, the back scattered power. Right, all the power that I'm increasing at the transmitter is just getting back reflected, and the received power remains the same. So if I plot some signal to noise ratio, right, which is the power at the receiver divided by noise power, right, so that basically increases in this linear regime, but beyond this threshold it starts reducing again, right, because beyond the threshold my receiver power is actually so it might even actually start going down a little bit because okay, so the SNR starts falling dramatically beyond this threshold input power. Okay. So again, if from a communications perspective, if I'm interested in, for example, low bit error rates, so high SNR, then the bit error rate will increase dramatically beyond this, right? So I want to be below 5 millivolts at the transmitter. Okay, so one way to overcome this in the initial days was basically one way that was discovered was what you can do is, so again, recall that this Brillouin gain line width is quite small, right? So we saw this was like 50 to 100 megahertz, right? And so far we've talked about sort of a single frequency getting scattered, right? But you know, for communications, actually, we actually put some data on it, right? So this has some finite bandwidth around the pump wavelength or frequency. Right, so you can imagine that, so in the initial days when the data rates were small, right? So below a gigabit per second or something, right? So this bandwidth here is basically roughly like the bit rate, right? So this is roughly the bit rate, right? So basically when in the initial days when the data rate was small, let's say like below a gigabit per second, then this was small enough to fit inside the this Brillouin gain line. Okay, so for all practical purposes, this acts like a particular frequency getting scattered to the stores, right? But now you can see that if I somehow make this very wide, right, then basically you can see that only a very small, when I Brillouin shift it, a very small portion of it would sort of be within the Brillouin gain. Okay. Right. So effectively, the the power that is getting backscattered is the power within this Brillouin gain line. Okay. So if I have a bandwidth which is larger, right? So effectively the threshold power scales. So instead of this, I have an additional factor, which is the ratio of my source bandwidth delta Fs to the Brillouin line width delta Fb. Okay, so basically I can shift this threshold to higher values, or in other words, send higher power without getting back reflected if my source bandwidth exceeds the Brillouin line, right? So you can see that actually for incoherent sources, right? It's not this is not a problem at all. So this Brillouin scattering was first noticed when people started using coherent or single frequency lasers, right? And that's when they started noticing this huge back reflection. So when the source bandwidth was very small, right? So the single frequency semiconductor lasers have this delta F below a megahertz. Okay. And then once you put data, of course, you have some bandwidth here. But for low data rates, like up to hundreds of megabit per second, this delta F, this bandwidth here is still comparable to delta FB. Okay, so you can still get significant backscattering. So in the initial days, what was done was there was additional phase modulation put on the laser, right? So you can increase the bandwidth, of course, just by putting direct data, which is intensity modulation. But also you can modulate the phase, right? So we had discussed this briefly for dispersion compensation, how we put chirp, for example. Similarly, if you put some phase modulation on the laser, right, then that phase modulation also leads to a broadening, right? So, so for example, if I modulate with at some particular frequency, again, if I send a microwave signal at a frequency omega m, right, I can broaden this by FM, right? So if my microwave signal to the phase modulator after the transmitter here is much bigger than 100 megahertz, then basically effectively the source bandwidth is broadened here. So in the initial days, typically when the data rates were still sort of in the hundreds of megabit per second, people used to put phase modulation on it at, let's say, a few gigahertz, so that now this full bandwidth is much bigger, right? So your delta fs is, let's say, a few gigahertz, your delta fb is 100 megahertz. So now you can see that this factor now is increased by, let's say, 2 orders of magnitude, right? So for example, if you make this 10 gigahertz, this is 100 megahertz, then this factor is now 100, and now from 5 milliwatt you go up to 500 milliwatt, right? So now you can send much more power without getting backscattered, so effectively increase your link length for the same power at the receiver, right? So that's how it was done in the initial days. Nowadays, actually, it's not a problem. It's sort of taken care of its own, right? Why? Again, now the data rates are pretty high, right? So now the data rates are themselves like tens of gigabit per second, right? So automatically now the modulated data has a bandwidth which is like 10 gigahertz or more, right? So my input signal here is now not a single frequency, but it has a very broad bandwidth. After I put the data, it has a bandwidth now of 10 gigahertz or more. So now you can see that the fraction of the power in the spectrum which is fitting in the Brillouin alignment is very small. Right? So this factor automatically now, just because of the data rate, is already above 100. Okay, so now this automatically is boosted up to 500 milliwatts. Okay. So typically, the powers used at the transmitters are in the tens of milliwatt range, right? So that's much less than this effective threshold now, which is like 500 milliwatt. Okay. And we'll see that these other nonlinear effects also give some limitation on the amount of power that I can send at the transmitter. And yeah, so for all of them, typically we sort of the transmitted powers are typically in the tens of milliwatt range. Okay, not certainly less than 100 milliwatt. So for all practical links, we don't go above that. Okay. Right. So you can imagine here, like, so if you only had linear loss, then you could think that, oh, so for a particular power at the receiver, I can keep increasing my transmitted power, right? And if I keep increasing my transmitted power, then I can keep increasing my link length, right? For some amount of loss, right? So that way, basically, for a particular data rate, for a particular receiver sensitivity, I could keep increasing the link length by keep increasing the transmitted power. But you can see that nonlinear effect starts limiting you, and you can't keep increasing the power to keep increasing the link length. Right? So it's not as bad as what you would expect here, few milliwatts. So because of this high data rates and large bandwidth, the threshold power is slightly higher, so hundreds of milliwatts instead of few milliwatts. But still, there is some threshold that you can't cross. Okay, so yeah, we'll end here. Any questions? Right. So for, one thing to notice here is that for linear effects, right, typically if I keep increasing my transmitted power, that helps me improve my SNR at the receiver, right, and helps me improve performance. But for nonlinear effects, you can see the effect is opposite. As I increase the power, actually SNR goes down. Okay, so there's some limit up to which I cannot keep increasing the power to keep improving my SNR. So that's the difference between linear and nonlinear. Like in, for example, wireless communications, like typical RF microwave communications, you don't have these nonlinear effects, right? Because the channel is just free space. And there, typically, you always gain by increasing the power in the transmitter. Not the case with optical fiber communication.